Hello everybody, welcome to my speed run of homework questions section 6 student version. We're going to try to beat the world record of 12 minutes and 11 seconds here today. So let's have at it. Question number 1, consider what happens when a flowing river turns a water mill. So if you haven't seen it, basically we've got a wheel. That's interesting. We've got a wheel, and there's some water, and the water makes the wheel. Well, I guess it would make the wheel turn this way if the water's flowing this way, which is how I imagined it. Okay, so the water turns the wheel. Nothing too complicated. The source of the energy is probably something that you guys felt like was a little bit obscure. It's not the water. The water is not the source of the energy. The water is actually the mobile substance that causes and enables the energy to transfer. So the water is that mobile substance. The source of the energy that makes the wheel turn is gravity, technically, right? If this is a river that's flowing, the river flows because there is a height difference between the top and the bottom, upstream and downstream of the river, and that's what causes the water to be moving. The thing receiving the energy input is the wheel. We're just going to keep all three E's there. Is the water used up by the mill? Well, no, obviously not. The water will not be used up by the mill. This analogy does work okay for our, as an analogy for charge and for electric circuits. In an electric circuit, the source of the energy is a electric pressure difference or a voltage from the battery. And the thing receiving the energy input, that would be our light bulbs or a fan or whatever it is that we're powering with our circuit. The substance that's carrying energy in a circuit is charge, which is electrons. And the mobile substance, that charge is not used up. It just passes through and causes something to happen. Okay, so this water wheel, water mill is kind of a decent analogy for this circuit. Okay, if we have a string of Christmas lights that has 12 bulbs connected in series, and each one is labeled at 2 watts, regardless of what is labeled there, the energy transformation that is happening is the charge gets energy from the power lines, and then it gives that energy to the lights. Okay, and those lights, they would then use that energy to make light and some heat. The rate at which energy is being supplied to the set of bulbs when they are all lit, well, we know that power is equal to current times voltage, but we also know that the power for one of these bulbs is 2 watts. And so that means that the power for all 12 of those bulbs would be 24 watts. Okay, because we have 12 bulbs, 2 watts each, so 24 watts total. If we pull one of the bulbs out, the current and the transfer of energy drop to 0. We have an open loop, so charge cannot flow, and energy cannot be transferred to any of the bulbs because the charge is not allowed to move in this case at all. Okay, now we're going to imagine that the circuit in question 2 is rewired so that those 12 bulbs are connected in parallel. When they were in series, right, so if they're in series like this, having a little trouble here. Okay, but if they are in series like that, then we can have 120 volts across all of the bulbs. But if they're in parallel, all of them have the whole voltage across them. Okay, so that is essentially the difference. If we connect them in parallel, now they all have this huge pressure difference across them. And since they have that big pressure difference, which this is not a drawing necessarily based on this problem, so I guess that's worth noting. Okay, since we had 12 bulbs that were connected in series, that means that now the voltage across each bulb is 12 times higher. So if they all had 1 volt across them, now they have 12 volts across them. And since their resistance hasn't changed, then the current through each bulb is going to be 12 times higher as well. Okay, so they have 12 times the voltage, which means they have 12 times the current. And since they have 12 times the voltage and 12 times the current, and power is current times voltage, that means that they have 144 times as much power in total. So the whole circuit uses 144 times as much power by connecting these bulbs in parallel as opposed to connecting them in series, which is obviously a lot more power. It had been using 24 volts. I don't even want to multiply 24 by 144. But you can if you want to. Okay, if we connect 2 bulbs in series and bulb A receives energy at a rate of 10 watts and bulb B at 30 watts, the one that's brighter, is going to be the one that uses more energy. Okay, because the energy is being turned into light. So if there's more energy, then there's more light. So that means that bulb B at 30 watts is the one that will be brighter. Which one has a greater current through the bulb? Well, this is kind of a trick question because these 2 bulbs are connected in series. Since they're connected in series, actually they both have the same current. And so this last one is a little bit weird, but I'm going to draw a picture and see if I can explain it. So here I've got bulb A, and here I've got bulb B. And bulb B is very, very bright, and bulb A is not very bright. Okay? Bulb A could be like our round bulb, where bulb B could be like our long bulb. When we place those in series, the long bulb is lit, and the round bulb is not lit when we place the long and the round bulb in series with each other. They have the same current, but one of them is using more energy and generating more light, and that happens to be the one with more resistance, so that is going to be bulb B. Okay, if we were to color code this, this has more resistance, and it has a higher pressure difference. Bulb B does. That's not the right color. Number 5, you are given 2 circuits with identical batteries. In one circuit, they are in series, in the other circuit they are in parallel. Well, like we looked at up here, if we put them in parallel, there's always going to be a higher voltage in parallel. And because there's always going to be a higher voltage, there's also always going to be a higher current. And so there will always be a higher power for any bulb placed in parallel as opposed to in series. Okay, so in the case of the round bulb, here if it's in series, it has a very low power, but if it's in parallel, it has a whole, 9 volts or whatever the voltage of our battery is across it. So that's definitely parallel. The long bulb, if we put it in parallel, it'll be red to blue, not orange to blue. So that's definitely going to be higher in parallel. And since both of those are higher in the parallel circuit, the battery will also have a higher power in the parallel circuit. Number 6, we are designing a 1000 watt hairdryer for use in homes. Explain what information and calculations will be needed and how you would use them. So we know that the power is equal to the current times the voltage. That means that in order to make the power 1000 watts, we have to know the current and the voltage. The voltage is usually, in most American homes, 120 watts. Okay, which means we can use this equation right here to find the necessary current. Once we have found this current, I'm actually going to go ahead and just draw on that. Once we have found that current, we can use Ohm's law, which says that V equals IR, to find the resistance. And that's all that we would need to do that. Okay, the last question. Here we have this circuit right here. It's a familiar circuit. We have seen it before, where we have 3 different parallel branches, actually kind of 4 parallel branches, since we could say that these are both individual branches. The current is going to be greatest through point Z and least through point Y. This branch here, having 2 bulbs in parallel, has less resistance than a single bulb, whereas this one with 2 bulbs in series has more resistance. If we placed a shorting wire across bulb 2 right here, okay, then all that's going to do is it's going to make the charge bypass bulb 2 as it flows through that second branch. Okay, that is going to make this bulb brighter. It will not, however, have any effect on these 2 because these branches, the resistance did not change, but on this branch the resistance got lower, and so the charge flow is going to increase through bulb 3. I believe that means that these 2, the energy consumption is going to remain the same. This bulb, the energy consumption increases, and this one, well, it would drop to 0 since the current through bulb number 2 would be 0. The current here would double, but the voltage would also double, so we would have an increase in power on the circuit by decreasing its overall resistance. If we put that across bulb number 5, right here, then we have given the circuit a path that exists where there is no resistance at all. Since there's no resistance at all, that means that our power is going to increase kind of, well, I think it drops to 0, but not exactly 0 because the wire is going to get hotter. This is kind of weird to talk about. In real life, the power would not be 0 because this wire here would get hot. In an ideal circuit where the resistance of the wire is 0, then it would be 0. time's up. This would decrease